What's going on, everyone? Welcome back. Patrick here, and moving on to another linear programming example. So we have to maximize z is equal to 3x plus 4y with these four restrictions, where x plus y is less than or equal to 12, 3x plus y is greater than or equal to 12, x plus 2y is greater than or equal to 9, and then y is greater than or equal to 2. So first thing that I'm going to do is graph these restrictions, graph these lines, and then find the region that's bounded by all of them. So starting with the first line, instead of writing it as the inequality, I'm going to write it as x plus y is equal to 12. And what I'm going to do is I'm actually going to find the intercepts, the y-intercept, the x-intercept, get those 2 points, and then just connect them in order to draw this line. You don't necessarily have to. That's what I'm going to do. So to find the y-intercept, we'd plug in 0 for x, and notice then we'll have 0 plus y is equal to 12, and we'd end up with y equaling 12. So we know 0 and 12 would be the y-intercept of this line here. And then the x-intercept, we'd plug in 0 for y. So when we plug in 0 for y, we'd end up with x equals 12. So 12 and 0 would be the x-intercept for this line over here, right? And so if we graph both of these, so let's make a graph here. Let's try to keep it as much to scale as possible. So we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then same thing up here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll have 0 and 12, and then we'll have 12 and 0 down here. And so connecting these points, we'd end up with that line right there. Now, that's just the line, but notice that this is an inequality, right? So x plus y is less than or equal to 12. So which region would we be looking at? Well, what we can do is we could isolate for the y, so bring the x over. So notice all the y values have to be less than negative x plus 12, which is this line over here. So since the y has to be less than or equal to, we'd be looking at this region over here. So I'm not going to shade it in. What I'll do is I'll just put an arrow for now. From this line here, we're looking at all the y values that are less than this line. If this was reversed, if the y values were greater than or equal to negative x plus 12, we'd be looking at this area over here. Right? So that's the first restriction. Now the second restriction, 3x plus y, again, I'm going to make it equal to 12 first, and then I'll deal with the inequality after. So let's find the y-intercept first. So plugging in 0 for x, notice we'd end up with y equaling 12. So it actually has this line here, 3x plus y is equal to 12. It actually has the same y-intercept as the first line, so 0 and 12. But the x-intercept is going to be different. So notice that if we want the x-intercept, we plug in 0 for y, so we'd end up with 3x plus 0 is equal to 12, which would be 3x is equal to 12, which means x is equal to 4. So 4 and 0 would be the x-intercept of this line, 3x plus y is equal to 12. So 4 and 0 would be over here. Right? And so if we connect these 2 points, we'd end up with that line. And notice that when we look at it as an inequality, isolating for the y, bring the 3x over, we'll have y is greater than or equal to negative 3x plus 12. So what we're looking at is all the y values that are greater than this line. So we'd be looking at this region over here. So I'm going to just draw an arrow like that, right? For this line here, we're looking at this region. For this line, we're looking at this region, right? So the region bounded by both lines would be this region over here, but we have more restrictions to bring in to make that region tighter. to see what's going to be bounded by all four restrictions. So moving on to the next, we'll have x plus 2y is, let's just deal with the line first. X plus 2y is equal to 9. So notice that if we want the y-intercept, we plug in 0 for x. So we'd have 2y is equal to 9. So y would be 9 over 2. Or that's 4.5. So 4.5, 1, 2, 3, 4, it would be over here. So that would be the point 0. And 9 over 2. And then if we want the corresponding x-intercept, plug in 0 for y, and we'd end up with x equaling 9. So 9 and 0 would be the x-intercept for this line, which would be over here. Right? So if we connect both of these, we'd end up with that right there. And notice that looking at the inequality, we're looking at all the y, or we're looking at when x plus 2y is greater than or equal to 9. So isolating for the y, bring the x over. Like that, divide everything by 2. Because we're dividing by a positive, we don't have to flip this sign. And we'd end up with that right there. So all the y values greater than or equal to this line, which is this line over here. So we'd be looking at this area right there. All right, so we're getting our region tighter and tighter. Now, the last restriction would be y is greater than or equal to 2. This one's pretty easy. What's y equals to? Well, that's just a horizontal line, which would be right over here, like that. You know what? Let me make this a little more horizontal just to kind of differentiate these 2 points here. So we'll have something like that. Right? So that's y is equal to 2. And from that, we're looking at all the y values above that. So we'd be looking at this region over here. And then I erased this arrow. But from this line, remember the arrow was like this. And so from here, we can tell what the region bounded is by these 4 restrictions, by these 4 inequalities. It would be this region over here. Because if we didn't have this line, then notice how this would just keep extending down. Right? But because it's bounded by this horizontal line, it makes that region smaller. So the region that we're looking at is this over here. And so notice, what are all the corners of the region? Because remember, once you have the region, which is the first step of a problem like this, the optimal solution, right, we're trying to maximize z is equal to 3x plus 4y. It's always going to happen on the corners, right? So it's going to be on this corner, or on this corner over here. Now, this point was pretty easy to get, right? It's just that y-intercept of the first 2 lines. But notice we're going to have to put in a little bit more work to find out what this point, and this point is. Even though this graph, we tried to make it to scale, you always want to check algebraically what these points are, just to make sure you're not making any mistakes. So starting with this first point here, let's find what that point is. So notice it's the point of intersection between this line and this line. Now this line here was the second line, 3x plus y is equal to 12. And notice that this line over here was the third line, x plus 2y is equal to 9. Right, so what we can do is solve the point of intersection with these, either with substitution or elimination. What I'm going to do is substitution, so I'll isolate for this x, and then I'll plug this here into this x. So we'll have 3 bracket 9 minus 2y plus y is equal to 12. So we'd have 27 minus 6y plus y is equal to 12, like that. And then what would happen is we can bring this 27 over, so we'd have negative 6y plus y is equal to 12 minus 27. Negative 5y equals, this here would end up 12 minus 27 would be negative 15. Divide both sides by negative 5, the y value would be 3. Right? And if we look at the graph, it makes sense that the y value would be 3. If you look at this point, it's, even though this is not like fully to scale, if you drew this on graph paper with exact scales, then you actually would get that exact point. But because this is just a rough sketch here, we can tell that y equals 3, getting that value makes sense on the graph. Then if we want the corresponding x value, we plug in this 3, either or. We could plug it in here since we already isolated for the x. And this would end up being 3. So this point here is 3 and 3. I'll label it right there, right? And it makes sense. X value of 3 right there from the rough sketch. So we got that point. Now let's move on to the next point. The next point would be this one over here. And notice that it's the intersection between this line, which is that third line, and then this horizontal line, right? The y is equal to 2 line. And so we'd be finding the point of intersection between y is equal to 2 and x plus 2y is equal to 9. So notice we could just take this y equals 2 and plug it in right there. So we'd have x plus 2 is equal to 9, x plus 4 is equal to 9, so that means x is equal to 5. Right, so 5 and 2 would be the point of intersection. We know that this point here has a y value of 2 because it's on that horizontal line, y is equal to 2. We just have to solve for that x value, which ended up being 5 and 2. And this isn't as much to scale on this drawing. This should be, if this was on graph paper, it'd be shifted a little bit more, and it'd be at this x value of 5. That's why I say you always want to do it algebraically, just to not rely strictly on the graph that you make. Right, so we got 5 and 2, and then this last point here, well, we know it has definitely a y value of 2 as well. We just have to find the corresponding x value, and it's the point of intersection between the line y equals 2 and this line over here, which is the first line, x plus y is equal to 12. Plug in y equals 2 here, x plus 2 is equal to 12, which means x is equal to 10. Right, so this point here is 10 and 2, like that. All right, so now what we have is the region that's bounded by these restrictions, which in my opinion is probably the toughest part to get, and we have the points of the corners of that region. Remember, the optimal solution is always going to happen on one of the corners, and there's 4 corners in this case. Okay, so now what we got to do, pretty simple, is just test all of these points. So we got x, we're going to have a corresponding y value, and then we want to see what's the z value going to be, which is 3x plus 4y. Right, so starting with this first point, we got an x value of 0 and a y value of 12. Well, if we plug it into this formula, 3 times 0 plus 4 times 12 would give us a z value of 48. Moving to the next point, 3 and 3. Plug in 3 here, plug in 3 here, we'd end up with 9 plus 12, which would give us 21. 5 and 2. Plug in 5 here, plug in 2 here, so we'd have 15 plus 8, which would give us 23. And then that final point, 10 and 2, plug in 10 over here, plug in 2 over here. That would be what? 30 plus 8, which would give us 38. And what are we trying to do? We're trying to maximize z. So out of all of these, which one is the highest z value? 48. So the maximum value for z happens at this point over here, 0 and 12, and then the max value, if they ask for it, is equal to 48.